Hey guys, this is Srini, and in today's video, let's talk about using UNit for semantic segmentation. And let's use the mitochondria dataset that's publicly available. I'll leave a link for you guys to practice this. Now, in fact, I have covered a series of videos on the topic of UNit. In fact, go back to video number 73, 74, 75, and so on. So you'll get a bit more understanding of what units are. And I did almost an in-depth review back in those videos. So here I'm going to mostly focus on the application and not dwell too much time talking about what units are. Although, if you haven't watched those, it does make sense for us to quickly have a look at what units are and then jump into the code. As usual, I'll share the code with you. So please focus on the video and practice on your own time. Find the link down below for the code for my GitHub page. And while you're there, go ahead and subscribe to this channel. Okay, first of all, UNit is a deep learning architecture. And why do we use it? Well, here is a quick snapshot. Especially for images like these that are kind of busy, right? If you try traditional machine learning or any other traditional methods, it can be very challenging to get decent results. Here is something I have done using the code I already used in many of my previous videos, where we extracted the features, using VGG16 or just otherwise, like using Gabor filters, but then use random forest and segment each pixel or perform semantic segmentation, right? And the results are not ideal, as you can see. I did exactly the same with UNit, which we'll do, of course. This is in this video, and you can see how much better the results are in detecting mitochondria in these electron microscope images. Now, this is an example with electron microscope images, but this does work with most type of obviously biological images, but also if you are doing drone imaging or remote sensing imaging in general, UNit can be a great architecture. Okay, now what do we mean by that? Well, if you want to know a lot more about units, go ahead and read the original paper here, and here is the title. And go ahead and Google search for this, and if you can write down this link, I'll actually leave that down in the comments, in the description, so you can go ahead and download this PDF and get even more information about UNit. Now, just at a high level, what is UNit, right? I mean, it's called UNit because it's in the form of a U, let's say the architecture. The input image goes in, and then you see these 64 filters, and then 128. As you can see, this gets smaller and smaller, and this gets wider and wider, and eventually the entire information is almost encoded. This is almost like encoder decoder, right? You have something that's going from 572 by 572 all the way down to like almost 30 pixels or so, and then like the entire thing is encoded into this one vector, and then we are actually going back, not vector, but let's say tensor, and we are going back up and reconstructing this image. And while we are doing this, we are actually concatenating information from this layer with this layer. You see, graphically it's represented here, and from this layer to this layer and this layer to that layer, right? And why is this better? Again, I briefly talked about this in my video number 73, and of course go ahead and read this paper. Now, in between you can see these operations of convolutional 3x3 ReLU and max pooling and so on. So this is the architecture for UNit. Now, if you actually code this in, it may look like lots of lines of code, but this is basically the standard implementation or the simple implementation of UNit, where you have like layer C1 and then layer C2, convolution 1, convolution 2, convolution 3. And one thing I'd like to highlight is if you go back, this entire thing, you see, this is all convolutional network. There is no dense layers, which means you're not forced to just use this for 572 by 572 pixel images. If you have 256 by 256, you can go ahead and use it, right? Like the standard. So what you do is define your standard, architecture, something like I've done here, right? You have a contraction path going down, and you have an expansive path going up. And in between, you're doing this concatenation of layers U6 and C4, right? So here there is a U6 layer, U is going up, and C4 is going down, right? So you kind of concatenate this information. You try this a couple of times, you'll get a hang of it. Now, If you really would like to use this for your own, let's say, different size images, when you want to, if you have 128 by 128 images for training, just change this image height, width, and image channel, and it should actually work. Okay, go ahead and print out the model summary to make sure everything makes sense, and we'll do that in a minute. Okay, so this is how you kind of write this in Keras. There are numerous implementations of these online. Go ahead and copy someone else's code if they have already written something like this, or just get mine, right? I mean, link is down below. And one other thing I'd like to mention is UNet is just the name of the architecture. How you change this, I mean, you can actually change this many ways. You can also, instead of using your own custom contraction path, you can, in theory, actually use something like VGG16 or MobileNet or any of the pre-trained architectures, and then instead of training that, go ahead and use that as your encoder path and only define the decoder, right? So you can do all these tricks again as long as you do this concatenations and combining these. So you got to be a bit better at actually imagining how this would look like if you put your own network. For this exercise, I'm going to use the standard unit, and it actually works amazingly well on most of the data sets, at least the ones I have tried. Okay. Now, what data set are we going to use? Again, here is the link to the data set. It's a electron microscopy images, a bunch of electron microscope images and corresponding labels. And you can download the training subvolume, and you can download the ground truth and the testing subvolume ground truth. Each of this image, I think in the subvolume is 1024 by 768, and you have 165 such images, and this actually works fine. And if you just go to this link, go ahead and download all this data, and you should be ready. Okay, so but these images are huge, like 1024 by 768, or if you work with the original images, they are 2K by 1.5K. It's very difficult to fit all of that into your memory, right, while you're training. So what I've done is I've taken all that and I've written my own script to divide these images into individual patches of 256 by 256, right? So I have more than 1,000 of these 256 by 256 patches and corresponding masks, right? You have to divide the mask, these images exactly the same way. So your mask matches your images, and this is exactly what I'm going to use for training. Now you can do your own tricks, but this is just to let you know, this is exactly what we are trying to use. Okay, given this information, let's actually jump in. I think that's the last slide. Let's actually jump in and get to work right now. Okay. And first of all, let's have a quick look at my folder structure. Like I said, I have my generated patches subdirectory, and in here I have all my images, all of my images. I think I have, about 1,600 images right there, and corresponding masks. Okay, there you go. Now, let's get to the point here. So here again, instead of actually using this or defining the model right in my main program, I actually created a separate Python file just with my model as a function, so I can import it. The plan is in this video, I'm going to show you this, and in the next couple of videos, I'm going to show you a couple of different tricks. For example, how do you apply this? Okay, we are going to train this on 256 by 256, right? Size images, but how do you apply this to larger images if you want to predict? So I plan on using the same model for a few videos, so it makes it easy to keep this as a separate function. Anyway, so this is the file called simpleunitmodel.py, and from now on I'm just going to import this, right? So all it has is just a simple function with the code I just showed you, and it returns the model at the end of it. Here I'm fixing my image height, image width, and image channels, which means I have to use 256 by 256 images for predictions, and later on I'll show you how you can work with different size images. So let's not worry about it for now. Let's jump to the main code. Okay, so the main code, again, you will be able to download this, so don't worry about writing it down yet. So let's go step by step as usual. First of all, importing simple unit model from simple unit model. Well, basically what it's saying is from this file called simple unit model, import my function called or method called simple unit model, right? So that's exactly how you import this model right there. And from now on, when I just call it, the entire function, you know, I can use it. This is a very nice way of managing your code. And let's go ahead and import all the other libraries that we may need, which is OS for, you know, basically navigating through our directories, OpenCV to open images, Pillow to resize images. I love Pillow library because it makes it easy to resize images, NumPy and Matplotlib. No surprises, right? Okay. Next step, image directory and mask directory. My image directory is generated patches/images. And why am I doing that? So I can walk through each file in these libraries, in these directories, and then add all the images as a list to my empty list that's down here. So, but first let's go ahead and define our size as 256 because I want to resize all my images to 256 if they're not already 256. I may not be resizing them. Yeah, I am resizing, but they're already 256 anyhow. But this could be a good sanity check in case you have some images that are not 256, okay? Now, let's go ahead and start our empty lists, image dataset and mask dataset, so we can capture all images into this list and then convert that to NumPy array, but wait for it. This is exactly the same process we followed in any of my semantic segmentation videos. So, but it's still worth watching. Okay, so my images is os.listdir image directory. We already defined our list directory. It's basically, you see, if I open my images, you can see image 0, 1, 2, 3, 4, and all of these images, right? So it walks through that image directory and then creates a list of images. Now, for each of the element in this list, right, that's what we are doing. Go ahead and read it and convert that into, Pillow right there, and into a Pillow object. Resize this, convert back into NumPy array. That's all we are trying to do, and append it to our image data set. And we are going to do exactly the same even with masks. Okay, so let's go ahead and run all of these. This may take a second because we have 1600 plus 1600, 3200 images. So let me go ahead and pause the, there you go, it's done. It's not that bad. Okay, so now what we have is images, 1600 of them, masks, 1600 of them as lists. Let's convert that to NumPy array so it's available for our deep learning, right, in the right format. So I'm going to convert that into NumPy array and then normalize the images because right now they are 8-bit images, meaning the values go from 0 to 255. Always scale or normalize your inputs when you're doing deep learning, and expand the dimensions by 1 so they're ready for my deep learning again. So once we run this, you'll see exactly what we are talking about. So our image data set is an array of float 64 because we normalized it. And I have 1600 images, each 256 by 256, and I expanded the dimensions by 1 to add this additional 1 because I'm only dealing with grayscale images. So, but if it is color images, you would have already had 256 by 256 by 3 if you actually read them as color. Okay. So 256 by 256 by 1, we have the format ready. Now let's go ahead and do exactly the same thing even for mask. And for mask, I'm doing exactly the same, and I'm dividing the mask by 255. This is, I believe, optional because the mask, in my case, the mask is 0 and 255, right? The actual background pixels are all 0. And the mitochondria areas, the labeled pixels are 255. So basically, this converts them into 0 and 1. That's all we are doing here. Okay, so if you look at your mask data set right there, we have again 1600, 256, 256 by 1. So the format, both are all ready. Now we just need to split them into training and testing data sets. Again, this is pretty standard, right? I mean, we do this all the time. And I'm only holding like 10% for testing. That's okay. And especially when it comes to semantic segmentation, I like to do a sanity check, meaning, okay, is my image and mask are they corresponding when I load the same number? So this you have to do this. If there is a mismatch, then obviously your results are going to look crappy and you wonder what's going on all the time. Okay, so let's go ahead and plot some random images. There you go. Okay, that seems to be matching fine. Let me run this again. I'm using random to just generate a random number, so and plot these images. Okay, that looks fine. Let me do one more. Okay, I think I'm happy right now. You see, there are no mitochondria there, so I see nothing. Okay, this is just a good sanity check right now. Okay, finally, we are all set. Now, let's define the model and train it. We are almost there. And remember, our model takes three parameters. Our function takes three parameters: image height, width, and image channels, right? So in this case, I'm going to read image height, width, and channels from my image data set, which would be basically 256, 256, and 1. So there you go. And now let's get our model. How do you get your model? Well, it's basically simple unit model: image height, image width, and image channel, right? So I'm going to run this function and then assign that to a model, right? So when I do this, it should print my model out, because remember, in our model right here, we actually did print model.summary. So it is executing the last line when it printed this model. Let's have a quick look at this. Let's go up. Okay, so my input is 256 by 256 by 1. We know that, right? I mean, that's our input. There is nothing to train. It's not connected. And then comes the convolutional layer. Okay, and 160 parameters in this convolutional layer. And 256, it generates 16 filters in that layer. Another 16 here. Well, it's actually dropping out, and convolutional here. So as you can see, it's going from 256 to 128 to 64, all the way down to 16 by 16 by 256. A very small sized tensor, let's say. It's not a single vector. And then we are upscaling it from 16, 16 to 56, 32, all the way back to our original image size. How many parameters need to be trained? 1.9 million parameters. Okay, so that's the summary of our unit model. Okay, so now that we have this, let us go ahead and train it. I'm not going to train it right now. I have already trained this. It's going to take a while, and I'll let you go ahead and do that. So I did train it and I saved the model. So how do we proceed? Let's go ahead and load the trained model. So what I've done is I actually trained this model for 50 epochs and added another 50 epochs after initial 50. So basically 150 epochs. But after the 50 epochs, it was doing pretty good anyhow. So I didn't need this. But anyway, let's go ahead and load this model, right? I mean, you know how to do that. Model.load weights. So let's go ahead and load this. So it's almost as if we just trained it. I'm ready. Okay. But go ahead and train it on you. Obviously, train it first. And I can check the accuracy still, right? I mean, because I loaded the trained model. So let's go ahead and check the accuracy. I believe it was pretty high. Now, for semantic segmentation, accuracy is not the right metric. Okay? Because you may have like the entire background matching, but the actual mitochondria not matching very well. But you have your background to be like 99% of your image is your background. So if it matches, then it's going to give you 99% accuracy. But is that really, I mean, what does that actually mean? So when it comes to semantic segmentation, again, please watch my video on the topic of intersection over union. That's exactly what we are going to look next. I cannot plot right here because I don't have this history saved. We haven't, trained it right now, but I can definitely calculate this IOU, which is predicting on test and looking at the actual values and then comparing those two. Now, one thing you'll see here is I'm setting a prediction threshold of a value of 0.5, meaning what comes out of this prediction. When we actually do a prediction, let's go back to our unit model. You see, you have your binary cross entropy as the loss function, accuracy. I thought I had, let's see, activation as sigmoid right there, right? So what you would get out here is basically a probability. Your prediction is a probability. So if I go back, it's important, sorry. let's go back to our, what do we call, YPRED, right? YPRED. If you look at this YPRED, it's a pretty large data set, but if you just look at the values here, it's actually, you see, it's not 0 or 1 or 0 or 255. It's actually some value between 0 and 1 because it's calculating probabilities at every pixel. Okay, but I'm setting a threshold of 0.5, saying that, hey, anything above 0.5, make it 1. Anything below 0.5, make it 0. So I'm kind of binarizing this data. That's pretty much it. So my YPRED threshold, if you can see down here, it's basically binary, right? It's false, 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 or true wherever it's a mitochondria pixel. Okay, now let's calculate intersection over union. Did I already do that? Yeah. So intersection over union is basically looking at my test and the original values versus the prediction, and then just calculating this IOU score. Okay, so we got about 87%, which is actually excellent for semantic segmentation. 87% of IOU score is not bad. That tells me that we are actually correctly labeling our mitochondria pixel, bulk of them as mitochondria, bulk of the background pixels as background. So that's a good sign right there. Okay, now let's go ahead, and we already imported this model, so we don't have to worry about it. But if you close this file and you are starting from scratch, you can start here, right? Go ahead and get the model. You know what get model is right there, and then load the whatever the pre-trained model is. The weights are. Okay, so let's go ahead and grab some random images just like we have done earlier, but then this time, instead of just viewing them, we are going to go ahead and do the prediction on these. And again, here I am setting a threshold of 0.5. Anything below 0.5, 0, anything above 0.5, white, okay, or bright or true. And let's also load a external image. This image is one of the images that we held out as testing, right? The 10%. And this image is something that's completely external. We haven't used it. And let's go ahead and see how it performs on these images. And let's plot them. Okay, that's what this part of the code actually does. So let's go ahead and have a quick look at it, at the results. Oh, plots are up here. That is amazing, don't you think? Isn't that pretty amazing? I mean, this is our one of the testing images, and here is the output, and here is our image that we just loaded, and it actually did a very good job. And if you're curious in terms of what happens if the threshold is, I don't know, 0.2, and let's change the threshold here to 0.2. I expect our mitochondria to be a bit fatter, but we'll find that out. Okay, let's go ahead and find that out. There you go. Yeah, you see they're a bit fatter, but this is very encouraging. Even if I go down to 0.2, that means our mitochondria pixels, we have very high probabilities, right? I mean, 0.5, even at 0.5, you're getting like very good separation, right? I mean, definition of our mitochondria. I mean, in this case, I can probably leave this to 0.2 or even go down to 0.1 to see where it's actually defining the real shape of mitochondria. But then please be careful that wherever you have these objects very close by, these two probably would be combined together, and you may have to find tricks to separate them. This is what we call instance segmentation. In fact, I'll record a video where we actually do this, intentionally get not so good segmentation, and then see how we can separate these objects to create a instance segmentation, and then do object properties, calculate object properties and report it. Okay, I promise to do that in the next 2 or 3 videos anyhow. Okay, so I hope this gives you a quick refresher in terms of unit and how you can apply this to your own images. All you need is literally this. All you need is images and corresponding masks. That's it. It doesn't matter if they are biological or if they are any other type of images. Usually this does a great job. So please test it out on your own samples, on your own images, and let others know by leaving a comment. And one final request, go ahead and like these videos if you like them, right? If you like them, like these videos, and subscribe to my channel. So thank you very much, and let's talk about unit again in the next video. Until then, please subscribe.